Okay, so hello and welcome again. So this time we're going to have another example on frames. So we have here two inclined members AB and CD supported by a roller and a pin at A and D. So we are going to determine the shear and moment diagram of this frame. And as usual, we are going to determine its reactions. We have a vertical at RE, a vertical RDY at D, and a horizontal reaction at D. Okay, we wanted to resolve this one, and of course we should be concerned on the distance of CD, which is also symmetrical to AB. And as we can see in the triangle, we have 3 horizontal, 4 vertical. Of course, this is obviously 5-meter length. So with that, we can say that this is 2 by 5, and that is 10, and it is concentrated along perpendicular to member CD. So of course we wanted to also determine the components so that we can work on the reactions. We have the vertical and the horizontal component of this 10. So we should have a reference angle. So we'll just have to take this horizontal angle here, the slope of CD along the horizontal line. And this theta should be transferred or referred to this triangle here on the components. So every now and then we have to recall our knowledge in transferring angles. So if we have an inclined and horizontal line, that is theta, and drawing a perpendicular plus a vertical line, this should be also equal to theta. So here we have, this is perpendicular and this is vertical, so that this is also theta. So remember that your uniformly distributed load here is locally placed at CD. When we say locally, it is perpendicular to whatever the axis of the member is. So now we are going to determine the vertical component of 10. And as we can see, it is clear that this is adjacent to our reference angle theta. So we just have to multiply it by cosine theta. And the other component is opposite the reference angle. And this is actually the projection of it. So you can see that this is opposite the angle theta. That is why it is expressed in terms of 10 sine of theta. Then we use the slope of 3, 4, 5 triangle in determining what is the numerical value of cosine theta or sine theta. So we have actually 3 horizontal, 4 vertical, and the line enclosing it is 5. And of course, this is our theta. So obviously, sine theta is 4 all over 5, and cosine theta is equal to 3 all over 5. Okay, so we're just gonna place that there. This is 3/5, and that is 4/5. This is calculated as 6, and the other component is 8. We are now ready to take moments at supports, determine the reaction. So we have summation moments at D is equal to 0, starting with this 10. Of course, we do not have to use the two components here because we have a perpendicular distance of this resultant from D, which is actually half of 5 or 2.5. And that would produce a counterclockwise moment. We have negative 10 times moment arm of 2.5. And then another is this 5. That is multiplied by the moment arm 3. Another counterclockwise moment, 10, by its moment arm that is equal to 5. And then another 5 here times moment arm of 7. And then the clockwise RE times moment arm of 10. So this shall be equal to 0. So your calculated RE is 12.5 kilonewton. So next, we sum up moments at E to solve for the reaction RDY. We have the clockwise 5 times 3, another clockwise 10 times 5, and another 5 by 7. Okay, so this time it is much feasible to use our components. So the yellow forces here. So it is not feasible to use this time this perpendicular force along CD because it's pretty obvious that we cannot determine the perpendicular distance of this force from A. So much better we are going to use this one. So starting with the vertical component, we have this 6 here will generate a clockwise rotation. So that is positive 6 times moment arm. So we have 3 plus 2, that is 5 plus 2, 7 plus half of 3, that is 8.5. So place it here, and then for the horizontal component of 10, we have a counterclockwise rotation. So that is negative 8 times the moment arm. Of course, obviously, this is just the half of 4. And that is equivalent to 2. And then this RDY, we have a counterclockwise times the moment arm of 10. And those will be equal to 0. So therefore, we will be having an RDY of 13.5 kilonewton. Okay, so of course you wanted to ensure that the correctness of your reaction by having the equilibrium equations along the vertical. We have these 3 downward forces, the downward component of this 10 here, plus the upward RE, and the upward 13.5. So those should be equal to 0, in which it's really equal to 0. So we are now ensured with our reactions. Finally, the horizontal component of the support at D is actually just simply equal to the magnitude of the leftward force caused by this result along CD. So that is 8 leftwards. Of course, it will just be countered by single horizontal force here, RDX. Okay, we'll just perform this, and it is pretty obvious that RDX is equal to 8. So we have obtained already our reaction. We replace or place the numerical value here, and we begin to have our analysis. Of course, we start from left to right, and obviously the first member is our member AB. Of course, AB here is detached from the whole structure. So when we do that, some portion of B here is cut or subjected to internal forces in our analysis. So first we label our external force. So the external force along AB is obviously, first we have 12.5, and then another force. You might think that 5 kilonewton could be included here along AB, but we must be very careful on that, considering 5 here cannot be or will be having a double loading if we consider it along AB and BC as well. So my tip here is just consider this concentrated load here, although it is located at the joint B. We'll just have to consider it just right of B. Therefore, it will just be included on the member BC or the beam at BC. So on our external force along AB, this will be countered by internal forces. So obviously this is downward 12.5, and our Horizontal force is obviously 0. We do not have any horizontal force here. And moment at B is yet to be computed. Of course, you wanted to place your joint there. And then we'll just take moments at B to solve for moment at B. Okay, so we do that. We have negative MB plus 12.5 times 3. So those are equal to 0. So we have here now 37.5 kilonewton meter for our couple at B. Okay, so we now proceed to the horizontal beam BC. Though we know that by and by we are going to get the components of these forces along the axis of AB and along its perpendicular axis. So we have to proceed with the horizontal beam BC here. Okay, say this is our member BC. Okay, we place initially these external forces and reflect the opposite or the reaction of this 12.5 coming from your first member, that's 12.5. So this is downwards, so it should be upwards when it is transferred on your beam. Similarly, we have for the couple, if this is a counterclockwise couple, so we place it in a clockwise manner on your beam. Okay, so we may place the value 37.5. So our next step is to first determine the internal reaction here, and obviously there is 12.5 here, this is 25 downwards. Of course, it is symmetrically placed on the beam, and obviously this shall be also 12.5. So basically 0 here is transferred here, no horizontal force at B, and it would follow that we do not have also horizontal at C. Of course, what will be the counter moment here? Okay, so we first assume the direction that this is clockwise. Say that is moment at C, and then we take moment at C. So a clockwise or a concave outward, I should say, we'll just have to pin this and then apply the moment. It will have a concave outwards that is considered as positive. So we just have to pin this MC, and then the 10 would have a negative or fiber is inward. So that is denoted by negative 10 times moment arm, 2 meters, less 5 times 4 meters, plus 37.5, plus 12.5 times 4. So those would be equal to 0. So we will obtain a negative value here. So meaning your MC is assumed incorrectly. So anyway, there will be no problem there. Just stick to your assumption and then of course carry the sign when you place it in your equation. Okay, so next we'll have the inclined member along CD. Okay, so we place the reactions here and then the resultant here with its component. So let us see. Okay, so vertical we have 6, okay, and horizontal is 8 here. We have 6 and 8. Okay, so we determine, okay, we just adapt what was computed here, just transfer it in here. So we just have a downward 12.5 here at C, and basing from your assumption here, just invert that one and then place your value with its sign. And as we can see here now, we check the vertical, the horizontal, and the couples. So it must yield to 0. So here Obviously that we have 8 leftwards, rightwards 8, so that will yield to 0 along the horizontal. And then for the vertical, we have an upwards 13.5, downwards 12.5, that will yield to 1. Of course, that will not be yielding to 0. So there's something wrong here in our analysis. So we go back to our beam here. So from your AB here, from the leftmost part, we have obtained 12.5 here. No problem with that. We just copy that one. Okay, so we have 20 here, downwards, upwards 12.5. So it shouldn't be 12.5 since we have here 20 minus 12.5. Okay, so it should be 7.5. Okay, so we'll place that one, we'll replace, and so as this one. Okay, so let us recheck. We have 7.5 plus downward 6, it is 13.5 actually. We have a single upwards force here that is also 13.5. So we just balanced our CD is just in equilibrium. Okay, so for the rotation, we will just have to check that in our moment diagram by and by. Okay, so the next step is, of course, before we proceed to the shear diagram, let us have a load diagram that is having all of the forces, internal or external, will be converted or expressed into components that is parallel to AB and perpendicular to the member, especially of those inclined members. Okay, we start with AB. So here it is. Here is our AB. We place the force. We place the component. Again, this is perpendicular and parallel to the member. We need to have a reference angle. Again, we'll be utilizing this angle. So here it is when it's transferred along this joint. So this is 12.5 cosine theta, and this is 12.5 sine theta. Okay, we recall our angles. So sine theta is 4/5 and cosine theta is 3/5. So your component here will be 10, and this is 7.5. Okay, we are done now with your joint A. So we'll proceed to joint B. Okay, so we also have the 12.5 here, and then the component, the reference angle, and the forces. Of course, is similar to the component of 12.5 here. We have 10 and 7.5. 7.5 is also adjacent to theta, and 10 is also opposite the reference angle theta, so similar to this. Okay, so we are now done with the inclined AB, so we proceed to the inclined CD. Okay, so we have this inclined member. So we first reflect here 7.5. Just extend this line for your reference. Again, we will be utilizing this angle here, so that if this is perpendicular and vertical, this is also our angle. Therefore, we now express this as 7.5 cosine theta, and this is 7.5 sine theta. Again, we replace it by corresponding values, so that this is 6 and this is 4.5. We will just have to place back our locally distributed load, because this one is already perpendicular to the member CD. Okay, so this is 2 kilonewton per meter. So we have the 13.5. It's perpendicular and vertical component. We use the same theta here, so that this is 13.5 cosine of theta, and this is 13.5 sine of theta. We place the value for cosine. and the value for sine, and this is 10.8. We also do that for the horizontal 8 here, and of course this will be the angle, the perpendicular component, and the parallel component of this 8. So this is 8 cosine theta and this is 8 sine theta. We place the values, and this is 4.8. Okay, so with this complete forces all resolved along the axis of CD and perpendicular to it, we are now ready to establish our shear diagram of this frame member by member. Okay, so starting with the AB. So this is AB. We have here an outward 7.5. So we will yield to 7.5 here, and then no loading, it will remain to be 7.5 until it will close to 0 here. Of course, we would want to reflect our moment or couple, internal couple, that is on B, and that is calculated to be 37.5. Okay, so we'll now proceed to the beam at BC. So for beam at BC, say this is our BC. So we look at the diagram here, load diagram. So an outwards 12.5. So of course this 12.5 will be countered by a downward 5 here. So the result is 12.5 less 5. And basically that will be an outward 7.5 here. It will remain until this point. So here it is, and then just left of this portion that is 7.5, just right of it, 10 would take effect and it will go 10 units downward. So from 7.5 minus 10, we have negative 2.5. Okay, so negative 2.5, no loading until C. So here it is. Okay, so C has 5 and 7.5. So an upward 7.5 less a downward 5 here will yield to positive 2.5, and that shall close this diagram. Okay, so moving on to the diagonal CD. Okay, so first we have here, so we have the inward 4.5, and then we less the area 5 by 2, that is 10. Okay, that is inward also. So negative 4.5 minus 10, that is negative 14.5. So we proceed to this joint. So obviously it should close it to 0. So as we can see here, 8.1 and 4.8 is yielding only to 12.9. So something is wrong with our component here. So in your 8.1 here, it is we used the angle. So 8.1 is actually perpendicular plus a vertical theta here. And then, okay, so the 8 here is horizontal. Okay, and we know that theta is along the horizontal. So this is the slope. Okay, so this is the slope, and then draw a horizontal line. Okay, so perhaps we have misplaced here the angle theta. So it should be the other side here. So this is the angle. Okay, so anyway, we'll just have to replace this one. So this is sine of theta instead, and this as well is cosine theta instead. Then we again place the values and the other values. So we compute for this one. We have this as 6.4. Okay, so this is still sine 4/5, and then this is the one we change with cosine. that is 3/5, and that is 4.8. So before we further proceed, we'll just have to check our rotated axis along whether it satisfies the equilibrium. Say this is x prime and y prime. So summation forces along x prime is right towards 6 here minus this force, which is 10.8, and then right towards here 4.8. So basically, if we subtract or sum up these numerical values, it will yield to 0. Okay, so we have just satisfied the equilibrium along the rotated axis x. We do the same for y. The summation forces y prime is equal to 0. First, we have here this going downwards 4.5, and then the downwards distributed load 2 by 5. So this shall be 2 by 5, and then the upwards 8.1 here, as well as the upward 6.4. So that should yield to 0. So this time it really yielded to 0. Okay, so I think we have a balance axis here, or equilibrium along those axes. So from 14.5 here, we have an upwards 8.1 and 6.4. This is actually 14.5. So it will just close our shear diagram. Okay, so we have now established our diagram. Perhaps we can get the area of this. So the area of this rectangular portion here, we note of this distance. So this is 5 by 7.5. We have 37.5. We also note the the distance here from this point up to this point. So this is 7.5 by 2. Obviously that is 15, and 2.5 by 2 here is 5. Okay, finally we have here a trapezoidal area. Again, we note the distance. So trapezoidal formula, b1 plus b2 all over 2 times the height. So we'll yield to 47.5. So note that this is a negative area as well as this one. Okay, so we now establish the moment diagram, starting again with AB. Here is our AB now. So this is a positive area that is equivalent to 37.5 up to this point. So this is a positive area. So we will have a positive 37.5 here. And the connector will just be a straight line. And then proceeding to BC, we have, okay, so we note that at joint B, we have computed actually a moment that is a positive in orientation. So negative, I should say, because if we are going to pin this and then apply this couple, it will tend to bend our frame inwards. So that is an inward, so therefore this should be negative 37.5. And from this, it will just close your diagram back to 0. Okay, so we also note that this 37.5 apparently will transfer to your beam BC, that is 37.5, and it will bend our beam outwards. So when it is outwards, that is denoted by a positive couple starting at B. So we do that. So we place it here, and then we also add here the positive area. So from 37.5 plus 15, we have 52.5, and the connector is just a straight line. And then we deduct again the 5 here, 52.5 minus 5, we have 47.5 again. connected by straight lines. So 47.5, we can see here that we have an MC. Okay, so the MC would tend to bring this inwards, or the beam inwards. However, this is a negative, so therefore it shall bring an outwards that would tend. Okay, we pin this down. Outwards the orientation, but that is negative. So in short, we pin this down, it will bring it downwards on the actual direction, because this is denoted by negative. So therefore, or just stick to this. Okay, we pin this and then apply the moment. It will orient our beam outwards, so that is positive. However, we carry the sign, so that is negative 47.5, and that will yield your diagram to 0. Okay, so here it is. We'll yield back to 0. Now for our shear or moment diagram based from this inclined member, perhaps we can move this in place here for a while and then proceed with the calculation. Okay, starting at your joint C. At your joint C here, we note the couple negative 47.5. Okay, although it will orient your frame outwards, that is positive, we carry again the sign. So we'll start with an ordinate of negative 47.5 at point C. Okay, so we place the value of the moment. That is so negative 47 denotes an outwards orientation of CD, so that is a positive 47.5. And then of course the negative area here will bring this back to 0. Okay, so how about the connector? So here we have decreasing slope here, so therefore if it is decreasing, we'll just use a concave downward connector. Okay, so this completes our shear and moment diagram. Okay, again, so let us have more practice on our home for us to sharpen our knowledge. So it is just but normal that along the way we commit errors, but errors could be checked by some parts of our solution, like if your shear diagram is not close to 0, or your reaction is not satisfying the equilibrium equation. So those are the mechanisms we have to look into along our analysis. So remember, along the way we commit mistakes, but to minimize the mistake, you have to check your solution by those mentioned mechanism to check your analysis. So stand by for another video on frames. Thank you for listening.